Hi guys. So in this lesson, I want to do some implicit differentiation. Now, firstly, what is it? Well, imagine a circle. So this is the equation of a circle with radius 3. X squared plus y squared equals 9. Now what we're used to, firstly, implicit and explicit equations. So when you have an equation y equals f of x, this is sometimes called an explicit equation. Whereas something like this, x squared plus y squared equals 9, is sometimes called an implicit equation. So it's basically where y is not expressed in terms of x on its own. So this is the equation of a circle. It is an implicit equation. And what I want to do is find the derivative. So what I want is, I want to be able to find the gradient of the curve at any point. So what I could do is, because remember, a circle is not a function, so what I could do is I could say y squared equals 9 minus x squared, y equals the square root of 9 minus x squared, and then this is either plus or minus that, and I can get two different derivatives, and I can use, so say for example I wanted to get the gradient of the curve at, let's say at x equals 2, it would be on my, it would be both this and, well, that's not great, it would be both this and this, depending if you wanted, because when x is 2, the curve is both here and here, if that was straight. So you could do it twice, and that would be called differentiating explicitly. But what I'm going to show you is a trick. Well, it's not a trick, it's a well-established, rigorous mathematical process, but whatever. Let's call it a trick for now. We are going to differentiate this implicitly. And what we do is, so we have x squared plus y squared equals 9. What we do is we get the derivative of the left and we get the derivative of the right. So we're doing the same thing to both sides of the equation. So I'm basically saying get d dx of this and get d dx of 9. Now we know the derivative of 9 is 0, and we know the derivative of x squared is 2x. So we get the derivative of the left and the derivative of the right. The derivative of the left, this bit, and it's with respect to x. So the derivative of x squared is 2x. We know that. Now this is the tricky bit. How do I differentiate y squared with respect to x? Well, remember, y is a function of x. So what we do is we use the chain rule, and the chain rule is we differentiate the outside function, which is 2 times y, and then we differentiate the inside function, which is y, and we multiply. So it's 2y times, what's the derivative of y? Well, it's just dy dx. And then the derivative of 9 equals 0. Now this bit, when you first see this is confusing. So let me go back to that. This is the only part that is new and that's confusing. And if you understand this, you'll be fine for the rest of it. Let me try and explain this with another example. Imagine instead of y squared, I want to differentiate sine x squared. So imagine, okay, this is a good way to explain it. Consider, now this is nothing to do with this question, I'm just using this example to help you understand it. Consider y equals sine x. Consider y equals sine of x, right? So what's the derivative d dx of sine x, the derivative of sine x squared. Well, what we do is we differentiate the outside function, which is the sine of x squared, so it becomes 2 times sine of x, and then we multiply it by the derivative of the inside function, so it's the derivative of sine x, which is cos x, so it becomes 2 sine x cos x, or 2 times y times dy dx. This is purely the chain rule. And if you think of y, that y is some function of x, and I use sine x here because it's a nice way to explain it, then you have to multiply by the derivative. So hopefully this makes sense, and if this makes sense, then this makes sense. Okay, fine. Now, once I have done that, I can get the derivative. I can say dy dx is equal to negative 2x over, it's negative 2x divided by 2y, which is actually equal to negative x over y. And that is my derivative. And it's a derivative in terms of x and y. So now when you're getting the derivative when x is 2, well, what you end up substituting into my derivative is my x value and my y value. Hence, I get there will only be one solution. It will give me, well, depending which one you want, but it will give me that solution because, or that gradient, because that I will sub in 2 for x and, well, what is it? The square root of 5 for y. And if I wanted this, the gradient of this, of the graph at this point, I'd sub in 2 and negative root 5. Okay, so that's kind of the theory of implicit differentiation. I want to do an example. It's pretty much taken from a past paper question. I've altered it very slightly, just the first part. I actually want us to get the derivative. Okay, so what we're going to do is we're going to differentiate the left and differentiate the right. So the derivative of y cubed, similar to how I differentiated y squared, I'm going to do 3 times y squared times dy dx. Same thing. Derivative of y cubed is 3y squared, and then I multiply by the derivative of y, which is just dy dx. Minus. Okay, now this is a product. I have 3x times y squared. This is the part of these questions that always causes lots of problems, because there's a minus here to begin with, there's a 3 here, and I've got my product with x and y squared. So I'm going to leave the minus there, and I'm going to put a bracket here. So my u, and you could actually take out the, well, why don't we do that actually? I can take out the 3 as well. I'll take out minus 3, and I'm going to do my product rule with x and y squared. Now I'm going to do the product rule over here to the right, like I always do. So u is equal to x, v is equal to y squared. Du dx equals 1, dv dx equals, okay, I need more space here. I have to be very, very, very careful. dv dx equals 2y dy dx. That's like my circle example above. 2y dy dx. You don't even need that dot there. Okay, now in the brackets, I'm going to put u times dv dx, x times dv dx, which is 2y. So if you don't mind, I'm going to put the 2 first. So it's 2x y dy dx. That's just this times this, plus v times du dx, which is just y squared times 1, which is just y squared. Close my bracket. Plus, what's the derivative of x cubed? Well, that's easy. It's just 3x squared. Now here we have another, let me just move this a bit over here. We have another situation here where we have a common mistake that occurs. You have to differentiate the right as well. So we differentiate the left and we differentiate the right. The common mistake is to put down 27. That is wrong. You have to differentiate 27, and the derivative of 27 is 0. Okay. Now I'm going to multiply all this out. But if I actually look at this, look, these 3's cancel. Nice. So let's cancel the 3's. 3, 3, 3. I'm dividing everything by 3, dividing across by 3. So now I have y squared dy dx. Careful with this minus. Minus 2xy dy dx minus y squared plus x squared equals 0. Now the first question says find dy dx. How do I find dy dx? Well, the terms that have dy dx in them are the first two terms. So I'm going to leave them here. So it's y squared dy dx minus 2xy dy dx equals, I'm going to add y squared to both sides. So y squared on the right, and I'm going to subtract x squared. Then I'm going to take out my dy dx because I'm trying to find dy dx on its own. So I factor out dy dx. I get y squared minus 2xy equals y squared minus x squared. And then finally, dy dx equals y squared minus x squared over y squared minus 2xy. Done. This is the derivative. Now this is the type of question I call familiar difficult. Definitely I'm not going to say that's an easy question, but I like that question, and I would like to see that in an exam, because if that question comes up in an exam, I'm thinking at least, well, I know how to do it. Yes, like there's plenty places for me to make mistakes, but it's the type of question that I've seen before and I know how to do it. Part B also is not too bad once you've done this. So it says find the coordinates of the points in the graph where dy dx equals 0. So this slight change I made to the past paper question was I actually said to find this. They just said this, find the coordinates on the graph where dy dx equals 0. And if they do that, it's a little bit easier, because you can just, even at this point here, you can just sub 0 for this and 0 for this, and you're just left with minus y squared plus x squared equals 0 and solve from there. But I could either do that, or now that I have dy dx, I can just do this as well. So it says find the coordinates of the points in the graph where dy dx equals 0. So let's do part B down here, part B. Dy dx equals 0. That means, look, this is my dy dx equals 0. That means the numerator, y squared minus x squared, has to equal 0. That means y squared equals x squared, and then y is equal to the square root of x squared, which is either plus or minus x. Okay, now, am I finished? No, I need to find the coordinates. What am I going to do? Well, this was my original curve. So let's bring that down here. Okay, this is my original curve. I need to find the coordinates where y is equal to x and negative x, and it satisfies this. So what I'm going to do is I am going to sub in x for y. So when y equals x, let's do this one first. When y equals x, so I'm going to sub in x. So now I have x cubed instead of y cubed, x cubed minus 3x times x squared plus x cubed equals 27. This is actually x cubed. is x cubed minus 3x cubed plus x cubed, which is minus x cubed, equals 27. X cubed equals negative 27. X is equal to the cubed root of negative 27. What's the cubed root of negative 27? Well, it's negative 3. So when x is equal to negative 3, y is equal to, therefore y is equal to negative 3. So my point is negative 3, negative 3. My second one is when, because remember y can be positive x or negative x. So when y equals negative x, I'm going to sub in negative x here. So I have negative x, don't forget my brackets, cubed, minus 3x negative x squared plus x cubed equals 27. Negative x cubed is negative x cubed. Minus 3, this becomes positive, so it's still minus, so it's minus 3x cubed plus x cubed equals 27. Those cancel. I'm left with, I can divide by negative 3 here, so I have x cubed equals negative 9. X cubed is equal to negative 9. Therefore, x is equal to the cubed root of negative 9. Now, this is a paper 1 question, and I don't have a calculator, so I'm just going to have to leave it as x is equal to the cubed root of 9. Therefore, y is equal to negative the cubed root of negative 9. So negative the cubed root of negative 9. And the point is therefore, the cubed root of negative 9, comma, negative the cubed root of negative 9, which equals the cubed root of negative 9, comma, the cubed root of 9. And the reason for that is because the cubed root of negative 9 will give me a negative number, and then it's minus that negative number, so it's a positive number, which is the same as the cubed root of 9. And as I don't have a calculator, I can't simplify that any further unless you know what the cubed root of 9 is. I don't. Okay, so that is implicit differentiation. Hopefully you'll see that it's actually easier to do it that way than to imagine me trying to write this equation out implicitly and then trying to figure out the derivative of that function. I want to just show you actually though, when I graph it, if I graph this, what I get. Well, look, this is the relation. You can see it's clearly not a function because it doesn't pass the vertical line test. But where is the gradient? Where is the derivative equal to 0? Where is the gradient equal to 0? Well, hopefully you can see it. It is here and here. Now, what are these points? Well, my solution where the derivative equals 0 was at negative 3, negative 3. So there should be 1 at y equals negative 3. So right here, or right where where x is negative 3 and y is negative 3, and yes, you can see it there. I can't actually click on that there, but oh, I can. Well, there, negative 3, negative 3. That this is a tangent to my curve. Look, you can clearly see it. Okay, and then this one is at, well, this was my y equals the cubed root. I can find the cubed root here. The cubed root of 9, remember it became positive, and there we go, same thing. You can see there that we have a tangent when y is equal to the cubed root of 9, and x is negative the cubed root of, or the cube root of negative 9, which is the same as negative the cube root of 9. Okay, that's it. That's implicit differentiation. Hopefully that made sense. Any questions, as always, let me know.